Hello everyone, welcome to my talk at the INNOQ Technology. I hope you've had a great day so far with our program and now you're hopefully ready for some hardcore mathematics, more specifically about theorems and how to get these theorems for free. So basically the idea of my talk is that everybody gets a free theorem. There's an unlimited supply of them, and I will, of course, talk about what that means precisely, what kind of theorems I'm talking about, and how to obtain them. So this talk will touch on two important papers in computer science. And the first paper is by John Reynolds. I apologize for this picture. I did not find any better one on that's really usable. John Reynolds described a theory of parametricity. And the second paper, this is Philip Wadler on the right side. He wrote a paper that's called Theorems for Free, so it's the eponymous paper for this talk, and he builds on this Reynolds parametricity concept and basically applies it to functional programming. Now, in order to get an idea of what they're actually talking about, we need to take a few steps back and first start talking about types. And more specifically, in this talk, I will be using Haskell as the programming language, just because all of the concepts can be quite easily explained and the type system is rather pure. Of course, all of these concepts can also be applied to other programming languages, and I will talk about this at the end of my talk. But in Haskell, for now, all of these concepts are very pure. So, basically, in Haskell, you have two things that you need to know is that type variables in Haskell are written in lowercase, and the second thing is all types are erased. So you kind of have a perfect type erasure where at runtime there is no trace left of the types that you wrote in your source program. And we will ignore type classes for now. They can be integrated into this entire framework, but they complicate things slightly, so we're just going to set them aside. And let's take a look at something that you could write in Haskell. So you could write the identity function and give it a name ID, and you write a type A to A, and A is a type variable, so you know this function works for all types. So you can call it on numbers and strings and whatever. This is what you would type and what the Haskell compiler would see. Now, the runtime, so the part of the system that will actually execute your program, will not see this A type here. Instead, it will just see some bytes or some words that are stored in some form, in some part of the memory of your computer. So according to the runtime system, you really have no polymorphism or something like that. It's all just words or pointers, something like that. So as you can see, there's nothing left of the original type information. In folklore, so when we look at various recommendations and suggestions in the Haskell community, the usual idea is that you should be using more type variables in your code. So you should try to avoid concrete types as far as possible, and whenever it's useful or whenever it's feasible even, use type variables, and this will make your program better. And this can be taken to some extremes, of course, in the Haskell community. So when we talk about some concepts like lenses for data access, we could be defining a lens as a pair of getter and setter with just two type variables. Or we could take another approach and could generalize this concept even further and introduce some extra type variables in there. Now, this is not meant as a criticism of this type signature. Actually, this is pretty nice to work with lenses like that. My point is that it is pervasive in the Haskell community that we try to generalize our concepts as far as possible. And of course, the drawback of this is that types become more abstract and we cannot immediately understand what's going on, but also this has some really nice advantages in other places, and this is what this talk is about. So basically what in this talk I'm trying to answer the question, why do we do this? Why do we use more type variables than might be immediately obvious? And the answer usually is, well, we can reason about those types. So if you have a concrete type, you cannot see much from it. That's the explanation. And if you have instead type variables, you can infer more stuff. But how is this possible? And this is exactly what Philip Wadler describes in the paper Theorems for Free. But in order to understand why this is possible, we need to go step back even further. So we need to abstract away from Haskell for now, and we need to look at mathematics. In particular, we would need to look at how sets work in mathematics. Now, just as a caveat here, set theory is just one possible way to look at this. There are also categorical views to look at this. But I'm not an expert in category theory, so I'm going to try to stay as far as possible at the source material and try to explain this based on sets. I'm sure there are other people who could explain this much better when looking at it or looking through a categorical lens. But for now, I'm just going to ignore that. Now, in set theory, almost everything is a set. For example, you can have the natural numbers, and that's a set. So 0, 1, 2, and so on. And if you go even deeper down the foundations, down this rabbit hole, you would find that even a number itself, like 0, can be defined as a set in set theory. But let's not go that far. We can take arbitrary objects basically and put them into set. That's the main idea. And it turns out that not only simple objects like numbers can be collected in a set, but also you can talk about functions sets. So let's consider this this function here. We have a set x and a set y, and the function maps items from the set x to the set y. So in this specific example, we would have a function that maps shapes to the color of those shapes. So we have a red triangle, and that red triangle is mapped to the color red because it's red. And or we would have the yellow rectangle, and it's mapped to the color yellow, and so on. And I guess functions are some ideas that everyone is familiar with, but we can also describe those functions as sets. And we can just look at all the pairs of input and output of those functions and, store them in a set. So here we would have a set that contains the tuple red triangle and red as color, and a yellow rectangle and yellow as a color, and so on. So yeah, this is so far pretty basic stuff. Of course, not all sets of pairs are functions. In particular, you can't have a function that maps the same input to two different outputs. That's forbidden. But if you don't do that, then it's a function. We can also look at Haskell types again, and we can try to motivate Haskell types by ascribing the sets of values to them that they describe. So for example, we can take a look at the type bool, and the type bool has exactly two values, true and false. So here we use these fancy brackets, and sometimes they are called denotational brackets because we're looking at the denotation of the type bool and say, well, the bool means we have two values, true and false. And whenever we see the type bool, you could equally think of, well, this expression has a set of two different possibilities at runtime. It could be a true or a false. And we can do that for pretty much all the types in Haskell. So we could, for example, also look at the denotation of the type integer, and then we would find that integers is basically a set of all the integers, starting from minus whatever, minus infinity, going all the way to plus infinity, basically. It contains all the integers. And I specifically used integer here and not int, because int are like machine words. They're capped at 32 bits or something, so let's just consider the real integers here. We can also do that for more abstract types in Haskell. So for example, the type of tuples, and you see A and B are unspecified here. So the denotation of the tuple type AB is the Cartesian product. And the Cartesian product in set theory basically means you take two sets and produce pairs, all combinations for pairs for these elements. So basically what you would expect. And also if you have a function type a to b, then that would be the set of all functions that go from the denotation of a to the denotation of b. So that that way you can define pretty much, you can define denotation for pretty much all the Haskell types. So the key insight here is that there are many different interpretations of types. So for example, we can just look at types from the point of view of a type checker. So from the point of view of a type checker, types are just like basically things that you can put into some kind of inference system. And you could see, well, if you have a function that maps integers to booleans, and you call this function with something of an unknown type, then the type checker can infer that the thing needs to be an integer, because otherwise you couldn't apply it to this function. But we can also take kind of a machine interpretation of types, and there it's just pointers basically. So this is what gets executed in our hardware. And the previous slide showed yet another interpretation of those types, and that would be mathematical or the set theoretic interpretation of types, where you can look at what types mean in an abstract set theory fashion. Now, just a quick side note here. Philip Wadler's paper uses denotation A star instead of the usual notation for lists. So in Haskell you would write lists with the square brackets, and Philip Wadler uses A star, and that's actually kind of interesting that there is a connection between the star that you know from regular expressions and the star that Philip Wadler uses, because in regular expressions we use the star, it means 0 or arbitrarily often of a particular thing, and that's basically what lists also are. You have 0 A's for 1 A or 2 A's and so on, and all of that can be unified into the same concept that's called a cleaning star. So that's some really interesting connection here that's going on, and this cleaning star can also be applied not just to types and regular expressions. There are a lot of other ways that cleaning stars appear in computer science. So that's a really interesting connection, but just as a side note. Okay, moving on. We have talked about sets. We have talked about how types can be interpreted as sets. We can look at the denotation of those types, and now we need to look at relations. Now, relations are also just sets, and the relation is essentially a set containing tuples from A and B, and then we can say one particular value of A is related to another particular value of B. And if we look at all of these possible relationships, we can build a whole relation out of that. One relation that you might know from real life would be parenthood. So you can check, you can define what a big relation of parenthood, and then A is related to B if A is a parent of B, for example. So, and we do that all the time in programming. Right, and it turns out that types cannot just be interpreted as sets, but types can also be interpreted as relations. So that might sound a little strange. So what do types relate with each other? Like, how does this work? And I'm going to define this just now, and it's going to be a little bit tricky. So I'm going to try to take a little extra time to explain what's going on here. Now, in the previous slide, you have seen the denotational brackets that have assigned every type a set, and that set is all the values that are represented by that type. In a similar fashion, we can assign a relation to every type, and we give this relation a particular name. We could just call it rel_t, and rel_t is supposed to be the relation that is ascribed to a particular type. Now, how do we define this? First of all, we can look at what is related to what else, And it turns out here's the connection between the set and the relation interpretation, because the relation rel t for type relates values of the type t to other values of that type t. So it's kind of a relationship between two equal sets. Now that sounds a little odd, and I agree, but let's just stay with this for a moment. If you look at ground types, so simple types like bool, integer, and so on, this relation is just the identity relation. So we just take the set interpretation and then relate that to itself. So rel bool would be the pairs true, true, and false, false. And for integer, it would be 0, 0, 1, 1, 2, 2, and so on. So there's really nothing overly fancy going here. It's just the identity relation. So we say that every value is related to itself and only to itself. So you cannot have 3 related to 5 or something like that with this rel integer definition. It becomes more interesting if we talk about relations that are defined on more complex types. And it gets interesting if these types are parameterized. So let's say we want to check if two lists, x's and y's, are related to each other, and they're not just lists, they're lists of A, some arbitrary A. And we could even consider checking if x's of type list of A and y's of type list of B are related somehow, but let's not get ahead of ourselves here. So assume that we have a relation for this A type, can be any relation, doesn't have to be one of the formally defined, can be anything. And now we need to check if those two lists are related. And how do we define this? Well, x and y's, those two lists need to be of the same length. And every element in those lists must be pairwise related. So the first element must be related to the first element, second to the second, third to the third, and so on. Let's look at this as an example. So let's say we have a particular relation where it says that the second element must, or the y must be double the x. Now we can look at different lists and see if they're related. So the empty list is always related to the empty list. Right? They have the same length, x 0, no elements in them to compare, check. The second line, we have two lists, equal length, so length is 2 in both cases. And the first list has 1, 2, and the second list has 2, 4. Now we check the first elements, 2 is double of 1, check. 4 is double of 2, also check. So those two lists are related. Next line, we have two lists. The list number 1 has 2 elements, list number 2 has 3 elements. So we have a mismatch of length. So those two lists cannot be related. No matter what relation we pick, if the sizes don't match, then they cannot be related. Finally, we have the two lists 1, 2 and 0, 0, 1. So in this case, the sizes are the same. But now we can try to figure out if the second list contains double the first list, and it doesn't, because 0 is not double of 1. So also in the final line, those two lists are not related. All right, so basically you can imagine if you want to compare two lists, you just write them one here and the other one down there, and then you just go element by element, you go through and check if all the elements are pairwise related. That's it. Now, same can be defined for functions, because functions are also some more also a more complex type, and we can have functions that take an input A and return an output B. And then we can ask the question, are those two functions of the same type A to B, are they related somehow? And the way we define this is that we say that two functions are related if they send related inputs to related outputs. Right? So basically the function would need to respect the input and output relation. So let's take the double example again. So two functions are related if when I give the second function the double of the first function, also the result would need to be double for the first function, for example. And of course, we can write this down formally. So we can say that f and g are related if for all pairs that are related inputs, the outputs of f and g are also related according to a relation. Now, at this point, in the audience, there might be two different reactions. So you might think, what the hell did I just see? This is just some simple mumbo jumbo. Like, what is the point of this talk? I don't like it. And the second reaction is, okay, you have talked so much about mathematics, but when will we get our free theorems? Like, we came here to demand free theorems. Where are they? And I hope I can put all of these pieces together now in the final session of this talk, when I will actually talk about parametricity. So I'm going to reap the benefits of all the mathematical introductions that I've just made. And we'll talk about the insight that John Reynolds had in his paper on parametricity. Now, what the parametricity theorem says, so this is the central theorem in the entire paper, it says that if you have some expression, some closed term, closed means there's no additional variables floating around, it needs to be closed, of a particular type, then this term t is related to itself. So if you have an integer expression, then you know that the expression is related to itself according to integer. So you know that t is equal to t. Well, that's hardly news, is it? Yeah, so what do we gain? Every term is related to itself. Cool. So we've just spent, like, I don't know, 20 minutes explaining some kind of set theory, and what do we gain from it? Terms are equal to themselves. Big deal. It's not a big deal yet, because it is indeed not interesting for integers, for example. But let's say we have functions on more complex types. So for example, let's say we have a function on lists. And Fromdicate is a function that takes a list of A and returns a list of A. Our parametricity theorem now says that Fromdicate is related to itself according to some kind of magic relationship. I'm not going to put this on the slide, so I just put a witch here on a broom. So we just say that Fromdicate is related to Fromdicate in some way. Now, what do we gain from this? Well, if we actually crank this entire theorem machine all the way to the end, this is what we get. We get a theorem about Fromdicate and map. So what this theorem says is that if we Fromdicate a list and then apply a map function g on this Fromdicated list, you will get the same result as if you had mapped the g on the input list first and then Fromdicated the result. So what that says is basically it doesn't matter if you first Fromdicate or first map, you will get the same result either way. So Fromdicate commutes with map. You can just change out, you can switch the operations around. And that's actually quite an interesting insight. In order to obtain this insight, we didn't need to look at the definition of Fromdicate. It's just something that we get for free based on the type signature of Fromdicate. So just by looking at the type signature, we know, oh, okay, the function takes a list of A and returns a list of A, we get the theorem. And if you look very closely at the theorem, it kind of makes sense because Fromdicate cannot do anything with the A. Everything it can do is drop elements, duplicate elements, or shuffle them around. It cannot make up new A's from scratch because it doesn't know how to make A's. It's just opaque. It's a type parameter. So Fromdicate can't do anything with it. And same goes for map. So map is also a function that the only thing it could do, it could drop stuff, it could reorder stuff, but everything it can do just comes from the A to B function that you pass it to. And we can all get that from just the type parameters. Now what? We have seen this for one concrete example, and I will now try to tell you how you can actually apply this in your Haskell code. So before, you might have just heard something about this reasoning about type stuff going on, and after this talk, I hope you can apply this to any function that you like. So I've already tried to summarize this in the previous slide. The basic idea is if you have a function that has a type that's not fully concrete, that contains type variables, this function doesn't know anything about a type variable and can't do much with the value of that type variable, right? So that's the basic idea, and that's kind of all the intuition we get about type variables, right? If we don't know the concrete type, we can't do anything with it. And in practice, we can apply this to a lot of different things. For example, we can prove that a second functor law is redundant. So just as a brief reminder, there are two functor laws as they are usually taught. So the first functor law is that if you map with the identity function, you get the same thing back. So map of ID is ID. Doesn't matter. If you map with ID, you can just not do it. The second functor law is when you compose functions. So if you fmap f and then you fmap g, you could have just fmap once with f point g, with the composition of f and g. And this law is what I claim here on the slide is redundant. So it turns out that you just have to prove the identity law, and that identity law then tells you that fmap does not shuffle elements, it doesn't drop elements, it doesn't duplicate elements in any way. And if that's clear, you know that all the elements that go in just go out unchanged. That's it. But because fmap has a polymorphic type, so it takes a function that goes from A to B, you know that the only way that it could have arrived at the output is by piping every single element of the input once through this mapping function. And if you know that, you can prove from that the fmap f, fmap g law, the second functor law, is completely redundant. You don't need to prove it. It just comes out of the first functor law plus the free theorem that you get from the fmap type signature. That's really nice. If you want to see that in action for some function that you thought of, there's a tool online. It's hosted on Joachim Breitner's website, and you can type in a type signature. So here I put in the type signature of the filter function, and then you can make some settings. For example, you can talk about, you can choose if you want to have recursion or not, because if you have arbitrary recursion, you could have non-termination, but let's set it aside for a moment. You can make all of these configuration options, and then at the end, you will get the free theorem from this type. And note that nowhere in this code you would need to, nowhere on this page you will need to define the function. You just give the type, and then in this case you also get a free theorem that talks about how you can either first filter and then map, or you can first map and then filter. It's really the same thing. And let's look at another free theorem. So if you have a function that has the type of map for list, so A to B, list of A, list of B, we can prove that this function is either map, so it could just literally be the map function, or it's a map function and then applied, and then we apply some rearrangement. So for example, it could reverse the input list, or it could just always return the empty list, something like that. But the point is, every such function can be expressed as map and then the rearrangement, right? So there's no other way for a function of this type to be implemented or to behave. That's really all it can do. Now, unfortunately, if we allow arbitrary recursion, like non-termination, it destroys everything. Well, almost everything. The problem is that if you have functions that can return bottoms, so throw exceptions, not terminate, and so on, the original parametricity theorem from Reynolds doesn't hold, because suddenly you can observe some subtle things. You could, for example, observe if an element of a list is bottom or not, something like that, basically. But it is possible to change the framework, to extend the framework to allow that, and then you will get the same theorems, but they will have preconditions. So you will say, well, map f is the same as f of map if the functions that you give are not, they do not return bottom, basically. But feel free to play around with that tool on Joachim's website, and you will see how the theorem is changed. Finally, there's another possible extension. So far we have ignored type classes because they complicate things a bit. In particular, let's say you have an EQ constraint. So if we remember the Fromdicate function, it takes a list of A and returns a list of A. If we give it an EQ constraint, it could do some additional stuff on the A. And in that case, we can't prove the original theorem anymore. And the reason is that EQ of A kind of gives additional power to a function, or it doesn't have to be EQ, can be OR or something like that. So if you have a function that takes an OR constraint, it could sort the elements in increasing order. And of course, if you first map and then sort, could be a completely different result than if you first sort and then map. So this could change. Now, usually the way this is addressed is by looking at classes as dictionaries. So if you have a function that takes some kind of class constraint, you would translate this class constraint as a dictionary. And the difficulty arises that these dictionaries might have rank 2 types. For example, if you pass in a functor dictionary, then you have some kind of nested quantifiers, and this is a little bit difficult to tackle, but there are papers on this that explain how this calculus can be extended accordingly. So bottom line is using this calculus works even for some more complicated Haskell definitions, but you will have to be a little bit more careful and have to do some extra work. Now, before I finish up with my talk, I would like to take a brief side note on applying this, what we have seen from Haskell, and use it in, let's say, Scala or in Java, for example. And the good news is that these theorems for free, it can be obtained in Java to some extent as well. But there you have additional restrictions because Java lets you introspect on objects at runtime. So Java does not have perfect type erasure. In Java, you can ask a thing what it is, and it will tell you, I'm a string, or I'm an integer, or something like that. And based on that, you can do stuff that shouldn't be possible to do. So if you write the identity function in Java, function that takes in an A and returns an A, you could look at the hash code of that A. You could look, you could say, well, if the hash code is odd, I would throw an exception. If the hash code is even, I'm going to system out print line and then return something. So all of that kind of destroys this reasoning. So if you want to apply this technique to Java programs or to Scala programs or whatever other language you have, you need to be very clear that these kinds of side effects are prohibited. Otherwise, the free theorems do not hold. But if you ignore all of these side effects or just don't use them, they're perfectly fine to be used within Java. And you can derive stuff like, well, if you map twice on a list, so if you have a list, map F, map G, it's the same thing as you've had just map once with the F point G or something like that. Or that you can commute, map, and filter, something like that. And all of these are optimizations that you can apply to your code. But because Java is such a complex language, it allows side effects, those optimizations cannot be applied by the compiler directly. Whereas in Haskell, the compiler actually applies some of these optimizations. So it will not infer them for you, but you can write them down as a comment in your code. And then Haskell will actually rewrite some expressions to be more efficient. And this is very frequently based on these free theorems. All right, well, I hope everyone got the free theorem that they liked. And if not, yeah, please do check out this online free theorem generator, type in the function you like, and get as many theorems that you want. Thank you.